All right, let's start talking about simple harmonic motion. Now, what you'll notice with the notes that are attached in this section on Google Classroom is that they're titled Waves and Sound, and that simple harmonic motion takes up about the first 5 to 6 pages there, and the rest is all dealing with waves and sound waves. Now, College Board scrapped including waves and sound in the AP1 curriculum just about a month ago. So we're only going to be focusing on those first 5 or 6 pages that deal with simple harmonic motion. And we're going to kind of jump around in order of the notes and, I'll expand in greater detail on some of the things like graphing in future videos. But for now, let's just look at the basics and talk about some basic vocabulary that you're going to see popping up again and again and again. And so if you look at the top of the notes there, right, we got these 5 terms: equilibrium position, restoring force, oscillation, period, and frequency. Right? Understanding what those 5 things mean is pretty much essential to understanding how simple harmonic motion works, right? How it behaves. So let's just start with that term oscillation. Now, an oscillation is any repetitive motion. So take, for instance, a pendulum that just swings from side to side. Right? Well, it's oscillating, right? It's got this repetitive motion of going from one end to the other, one end to the other, one end to the other, right? Or if we take a look at a spring, right? We pop that spring on there, pull it down, and it's going to oscillate around some central location. Now, these central locations are what we call the equilibrium position. So in the case of a spring, your equilibrium position is wherever it is unstretched, right? So this green line here indicates where the equilibrium position is on this spring. And if I pull it down to some amplitude, and amplitude just means how far off of equilibrium we pull it, right? It's going to oscillate around your equilibrium position. And your equilibrium position is where it will eventually come to rest if there are outside forces acting on it, right? So you'll notice that I've turned gravity off. That way, this just behaves as if it's a spring bobbing back and forth on a table. If we're looking at our pendulum, well, the equilibrium position is where the pendulum naturally hangs, right? We pull it some amplitude off the equilibrium position, and it oscillates around that central point. Now, the reason it oscillates around that equilibrium position is because there's something that we call restoring force acting on it. So, in the case of your pendulum, the restoring force here is the force of gravity, right? So, if we slow this down, gravity's pulling it down towards equilibrium. Its inertia moves it past it, and gravity pulls it back down towards equilibrium. But again, the object has inertia, moves past it, and you get that repetitive cycle, right? And again, notice there's no friction on, so that there is no loss of energy. If we're talking about our mass bobbing on a spring, well, the restorative force there is the spring force within the spring itself, right? So again, when we're dealing with springs, you're going to have to deal with Hooke's law again, right? F equals kx. Um, we went over that last unit. But so, yeah, you've got a restorative force that causes this object to oscillate around a central equilibrium point. Now, the other 2 terms that will not go away for the next 3 units are period and frequency. And your period, designated by a capital T, is equal to 1 over your frequency, and your frequency is equal to 1 over your period. So notice that your period and your frequency have an inverse relationship. Now, the period is the amount of time it takes to complete one full cycle, right? And so that's going to be measured in seconds. Whereas the frequency is how many cycles occur per second, and that's going to be measured in hertz. So hertz is going to be capital H, lowercase z, which is just an inverse second. Right, and it's an inverse second because notice frequency is 1 over period. Period is measured in seconds, so 1 over second gives you that inverse seconds, or the unit we created for it called hertz. So period is seconds per cycle, whereas frequency is cycles per second. So if we take it back to our pendulum, we'll put it in normal. If we want the period of this pendulum, so grab it, we're going to release it from here, right? So the period would be how long it takes for that pendulum to go through equilibrium, reach its maximum negative amplitude, and then return all the way back to where it started. So that would have been one period, however much time it took for it to go through equilibrium here and then return. So if that took, let's say, 2 seconds, your period is 2 seconds. Whereas your frequency is how many times per second it completes that back and forth motion. So if it completes a motion from here to here to here, so let's go one. Sorry, stop, stop. All right, so we release it. It goes boom, one, boom, 2 cycles, 3 cycles, 4 cycles. And let's say all of that occurred within 1 second. Well, then your frequency would be 4 cycles per over 1 second, right? Which would give you 4 hertz, right? So again, frequency is how many times a full complete cycle happens per second. So the entire there and back again. So let's take a look at example 14.1. So we want, it's called the frequency and period of a radio station. So an FM radio station broadcasts an oscillating radio wave at a frequency of 100 megahertz. We want to know the period of the oscillation. All right, so your radio station is broadcasting at 100 megahertz, right? So they've given you the frequency. So 100 megahertz would be 100 times 10 to the 6 hertz, and we want frequency. So if period is 1 over frequency, well, your period is 1 over 100 times 10 to the 6 hertz. And so your period comes out to be 1 times 10 to the negative 8th seconds. So again, you've got that inverse relationship, right? So the greater the frequency, the lower the period. The lower the frequency, the greater the period, right? So you have that nice inverse relationship there. So now let's talk just basically about what we mean when we're talking about simple harmonic motion. So simple harmonic motion is anything that, when you graph it, demonstrates a nice sinusoidal oscillation, right? And sinusoidal just means a graph that has the shape of a sine or cosine function. And we'll get into the graphing very heavily in the next video, so we're just gonna kind of skip over the graph section for now. But your two typical examples of simple harmonic motion are springs and pendula. So basically, anything that's operating in a state of simple harmonic motion, we can boil down to it's either behaving like a pendulum rocking back and forth, or it's behaving like a mass that's bobbing on a spring. So, take for instance, in the notes, they keep showing you a ball, a little marble that rolls back and forth in a bowl. Well, that marble rolling back and forth in the bowl, we can basically boil down to it's acting like a pendulum. Yeah, it doesn't matter that there's no string there. Its behavior, though, is pendulum like behavior. So, whether we're talking about the motion of an animal's legs while they're walking, that's a pendulum behavior, or the oscillation within the eardrum of your ear, that acts like a mass bobbing on a spring. So anything that undergoes simple harmonic motion, we're going to boil down into one of those two categories. Um, So take a look at example 14.1. We got two oscillating systems. They have periods 1 and 2, and period 1 is less than period 2. How are the frequencies of the two systems related? So take a second, pause the video, see if you can't figure that out. All right, so because of that inverse relationship, we know that if period 1 is less than period 2, then the answer's got to be C, frequency 1 is greater than frequency 2. Because again, you have that inverse relationship between your period and your frequency. And again, I was throwing that term around earlier in the video when I was talking about the pendulum and the spring um, simulations. Right, amplitude just means how far off of equilibrium position something is displaced. Right, so if you want to see that again, just roll back the video. All right, so we're going to skip on down to the notes to the formula for finding your period on a spring and a pendulum. So if we're looking for the period of something that's oscillating on a spring, well, the period of something on a spring is equal to 2 pi times the square root of the mass over k. And again, k here is your spring constant. So basically what we're saying is that anything that oscillates back and forth on a spring depends on two things, the mass of the object and how stiff the spring is. Whereas if we're looking at a pendulum, it's 2 pi times the square root of length over g. So the period of your pendulum depends on the length of the string itself and the acceleration due to gravity. Now notice the mass of the bob and the angle of drop don't matter when we're talking about the pendulum or the period of a pendulum, right? All that matters is how long is the string and what is the acceleration due to gravity. So the amplitude doesn't matter when you're talking about your pendulum period. So take a look at conceptual example 14.6. All right, an astronaut measures her mass each day using the body mass measurement device. During an 8-day flight, her mass steadily decreases. How does this change the frequency of her oscillatory motion of the device? So take a second, pause the video, see if you can't figure that out. All right, so if we want to know the solution here, we want to look at our equation for the period of a spring. So as she's bobbing back and forth on that chair, right, it's acting like a mass bobbing on a spring. So her mass decreases over that flight, right? So as her mass decreases, the period of the spring decreases. Now, if the period decreases, then the frequency increases because they're inversely related. So as she loses mass, she's going to increase the frequency with which that chair bobs back and forth. Now take a look at Stop to Think 14.5, where we've got 4 different mass spring systems, and they have masses and spring constants as shown to the right. We want to rank in order from highest to lowest the frequencies of the oscillations. So take a couple minutes, pause the video, see if you can't rank those from highest to lowest by frequency. Alright, so the easiest way to go about this is start by just looking at the period, right? Rank them by period, and then just flip the order to find the ranking by frequency. So let's look at the period for each one of these. So the period for A would be 2 pi times the square root of 4m over k. The period for B would be 2 pi times the square root of 2m over k. Period of C would be t equals 2 pi times the square root of 2m over k. And the period of D would be 2 pi times the square root of m over k. Now, obviously, they all share the 2 pi square root, so all we're really caring about is what's inside that square root. So if we're ranking it by period, so we'll put period right there, and then we'll put frequency right here. If we're ranking it by period, this one would have the greatest period, these two would be tied, and this one would have the least. Now, if we're looking by frequency, it's going to be inverse. Right, so whichever one has the greatest period has the lowest frequency. Alright, so if you're asked to rank things by frequency, rank them by period, then just flip the order. And so lastly for this video, let's take a look at 2 quick mathematical examples. So in example 1410, designing a pendulum for a clock. A grandfather clock is designed so that one swing of the pendulum in either direction takes 1 second. We want to know what is the length of the pendulum. Alright, let's just start by listing what we know. So one swing of the pendulum in either direction takes 1 second. Now, what they've basically told you there is that to go from here to here is 1 second. But that's not the period, right? The period would be coming all the way back to where it started, right? So 1 second, 1 second, your period is 2. So we know our period is 2 seconds. We want to know the length of the pendulum. Alright, so t equals 2 pi times the square root of length over g. So 2 seconds equals 2 pi times the square root of length over g. And solve out for length. And you get a pendulum length of 0.99 meters. Alright, let's take a look at 1411, finding the frequency of a swinging leg. So a student in a biomechanics lab measures the length of his leg from hip to heel to be 0.9 meters. What is the frequency of the pendulum motion of the student's leg, and what is the period? So basically, as this kid swings his leg, it's behaving like a pendulum. So we know that the length of his leg, or the pendulum, right, if we consider it to be that, is 0.9 meters. We want period, we want frequency. So the period is going to be 2 pi times the square root of L over G. So period would be 2 pi times 0.9 meters over G. So our period comes out to 1.9 seconds. And so if we want the frequency is just the inverse of your period. So 1 over 1.9 seconds. So our frequency comes out to 0.525 hertz. Alright, so I'm going to also upload on Monday morning the a set of problems that will deal with the um, 2 equations we're dealing with here. Keep in mind with the spring period equation, you may also need to use Hooke's law at times, at F equals kx. And then the next video will go in depth into graphing position and velocity and acceleration, and then defining how to calculate those. So hope all is well, and I'll see you all soon.